Okay, today we're looking at 2.4.2.5. We're going to be working on transformations of functions. That means reflecting and compressing or stretching and then shifting horizontally or vertically the basic parent function. So we'll learn how to do that today. Take a basic parent function and move it. So we will start with piecewise defined functions. Piecewise defined functions, different equations on different parts of the domain. Sometimes when we're doing maybe statistical data, we might collect some data and see that over a certain domain, one function is the best fit, and over another domain, a different function is the best fit. And so we maybe define the function in different parts to suit the different parts of the data set. So piecewise defined function. We'll go ahead and look at those first. So we have f of x equals x squared if x is less than or equal to 1. That's just saying that if I were to graph my first one without the restriction of x is less than or equal to 1, it would look like this, just as a parent graph that is a parabola going through the origin here. And then the other one is f of x equals x plus 2. That would be a linear function going through a y-intercept of 2 and having a slope of 1. So if we're to go over 1 and up 1, or down 1 and left 1, I could draw in that line. So those are my two functions. One is quadratic, one is linear. And we're going to combine those two together using the restrictions. So here's typically what I do is I look at the restriction here, and whether it's including the 1 or not including it, we can still plot that point, and that operates as our right endpoint for the first function because it says that this function is the model for all x values up to and including 1. So if I plug 1 into my function, 1 squared equals 1, so I have as a coordinate when x is 1, y is 1. So at 1, 1, I have a dot here. And so really what I'm doing is taking this function over here and only graphing the portion of this function that goes from that dot at 1, 1 to the left. And so back over here, I know it goes through 0, 0, and then if I plug in negative 1 to x squared, I get positive 1. If I plug in negative 2, I get positive 4. So fairly accurate left half of that piecewise function. Now at x equals 1, it's going to change. It says here that x equals 1 is not included. Now I'm still going to plug it in. If I plugged it in to my function, 1 plus 2 would give me 3. So when x equals 1, on the second function I'm all the way up at 3, and I put an open circle there because this is strictly less than, or is saying x is strictly greater than 1. So the other endpoint of this would be when x is 4. And since this is a linear function, that's going to be enough to graph it. If I plug in 4 for x, then add 2, I get 6. So I have another coordinate at an x value of 4 and a y value of 6. That puts me up here just off the graph. So here's 6 up here. And if I draw in that line, there's my piecewise function. You can see that it is a parabola to the left of 1 and then jumps up to here, to this open circle up here, and then is the line x plus 2 to the right of that. So once again, I like to plug in the endpoints of it, maybe fill in some values in between if it's a curve, and that gives you a picture of the piecewise defined function. So you'll be asked to go both directions. Given the function, draw the graph. Also, given the graph or information about the graph, write a piecewise function. So that's what we're going to do in number 2. It says write a piecewise function, defined function that represents the income tax law. What is the domain of the function? So here we have 3 different lines, here, here, and here, and we can graph each one by making the statement f of x equals, and then we do a big set notation here, it says when the annual income is less than $2,000, the amount of income tax is 0. So if you had an income of $1,999, or if you had an income of $60 for the entire year, anywhere up to, but not including $2,000, you would owe 0. So it's 0, and that is if x is less than 2,000. Give myself a little more room here. So we've got f of x is 0, and that is if x is less than, strictly less than 2,000. Now, if the annual income is between $2,000 and $6,000, it says you get 2% of the income over, or the amount of tax is 2% of the income over $2,000. So oftentimes what I'll do is write the restriction first and then write the equation after. But it says for an annual income of $2,000 to $6,000. So that is inclusive. We've got that statement, x is between 2,000 and 6,000 inclusive, and then we need to write a bit of an equation here. It says 2% of the income over $2,000. So what we're going to do is subtract $2,000 from the annual income. So for example, if the annual income is $3,000, we only want to take 2% of the money above 2,000. So 3,000 minus 2,000 would be 1,000. So we'd take 0.02 of that 1,000. So it looks like this: 0.02 times x minus 2,000. And I'm going to put a little semicolon there. So it's the equation is take 2% or 0.02 times the amount above 2,000. So that's why we have the x minus 2,000 there. So like I said, if you had $3,000 as your annual income, you'd go 3,000 minus 2,000, which is 1,000. You'd take 2% of $1,000. 10% of $1,000 would be $100. So 2% of $1,000 is going to be less than, it's going to be just $20. And that would be your annual tax, or amount of tax. Then it says for anything more than, strictly more than, so this is if x is greater than $6,000, then you have to pay $80 plus 5% of income over $6,000. So that would look like this. It's 0.05 x minus 6,000, and then plus, I've got to move all this down here. Give me a moment here. Roll this down. So there's my second one. There's my first one. So 0 if x is less than 2,000. 0.02 times x minus 2,000 if x is between 2,000 and 6,000. And then if x is greater than 6,000, we pay 0.05 times the amount of money you made for the year above $6,000, and then plus 80. And that's if x is greater than 6,000. So that's our piecewise function that defines the amount of tax that you would have to pay. All right. I'm going to move on to something you've worked with before, especially with quadratic functions. You've taken a quadratic function, probably in vertex form, and you've reflected it, maybe stretched it or compressed it, and then also vertically shifted it or horizontally shifted it. There are some set rules. So we can take that parent graph sheet, the yellow sheet, if you could take that out right now actually, and take any of those functions and apply these rules to those functions and move that function over. So for example, you could take, well, let's back up a minute here. If you take the parabola, for example, and if it's written in vertex form, we know that a negative out in front of the parabola will flip it over the x-axis. And if we have in parentheses in vertex form well, let me just show you here what it looks like. We'll go back. So let me list all the different types of shifting here. So we have a vertical shift. If we know that the function f of x is, say, a parabola, and we add or subtract a number to it, that's going to shift it up or down, depending on if we're adding or subtracting a value. A horizontal shift of any of our parent graphs would mean you're plugging in for x in function notation the expression x plus a number or x minus a number, and that will move it left or right. If you plug in, if it's x plus c here, it will actually move it to the left, and if it's x minus c, it will move it to the right. You may remember that you go the opposite direction of what you see in parentheses. I will give you an example of that in a minute. It looks like I have them underneath this. Reflection, negative f of x will reflect over the x-axis. F of negative x will reflect over the y-axis. And stretching, compressing is on the next page. I have that broken down for you. And there are some rules in terms of the value of c. Let's give you some examples here. Vertical shift. If we take the parent graph, x squared, that's a parabola, and add 1 to it, it's going to move it up 1 unit. Its vertex would be at the origin for the parent graph, and you would move the vertex up to the point 0,1. The one below it, h of x equals absolute value of x minus 2. Subtracting 2 from that would move it down 2 units. You can try that on your calculator. Just plug in those functions and look at them, see how it shifts it up and down. Horizontal shift. As I said before, this is actually the cubic function. R of x equals x cubed. That's the parent graph. When we replace x with x plus 3, it will shift the cubic 3 units to the left. B of x equals square root of x minus 4 is a square root function. When we replace x in the parent graph, which is just square root of x, with x minus 4, it moves the graph 4 units to the right. All right, f of x equals negative square root of x. That's going to flip over the x-axis. And t of x equals square root of negative x. Notice I'm replacing x with negative x, so placing it inside of the parentheses. That will flip it over the y-axis. So I'm going to give you a moment. You might want to pause the video and try graphing each of these examples. Graph the parent graph, and then graph the the transformed graph and see what it does to each one. So go ahead and take some time to do that, and then we'll talk about stretching and compressing. All right, we're going to look at some stretching and compressing rules here. It says g of x equals c times f of x. If c, that number in front of the function, is greater than 1, strictly greater than 1, you have a vertical stretch by c. If c is between 0 and 1, still positive, but a fractional value between 0 and 1, you have a vertical compression by c. If g of x equals f of c times x, in other words, you have a constant c being multiplied by the variable x inside the parentheses, if c is greater than 1, we have a horizontal compression by 1 over c. And if c is between 0 and 1, we have a horizontal stretch by 1 over c. And so if you could add all of that into the stretches and compressions part of your table there, that's a good summary. You'll be given the opportunity to play around with these on your graphing calculators in just a moment, so we'll try that next here. All right. Okay, we're going to use colors here. It says f of x equals negative x plus 4 squared plus 3. So you can see the parent graph for that would be y equals x squared, or f of x equals x squared. It's a parabola. And so what we're going to do, let me go through this, is start the graphing grid. We're going to start with one color. I'll use red to graph my parent graph. So my parent graph is y equals x squared. It looks like this. And we can use a different color for each stage if we want to. If you want an order in which to do this, just to be consistent, the order can be altered. You got to be careful about altering the order, but it can be altered and still get the same answer. But if you want to be consistent on this, what you can do is use the following order. Go ahead and do reflection first, so reflect. And then number 2, go ahead and do any compressions or stretches. And then 3, do your shifting, either vertically or horizontally. So if you want to be consistent, that'll work each time. So I'm going to go ahead and reflect this over the x-axis because of the negative out in front here. Then we're going to look for any kind of compressions or stretches. There aren't any. That's a -1 in front of the x squared term. It's not going to do anything in terms of compressing or stretching it at this point. So the next thing we'll do is deal with our shifts. So we have, in this case, a shift 3 units, 3 units. I'll do the 4 units left first. So we're going to go 4 units left first. So if we go 4 units left, go, let me go ahead and mark these off. 1, 2, 3, 4. So that would move this green one over to here, 4 units left. And then 1, 2, 3 up. So I have a horizontal shift of 4 units left because of this value here, and a vertical shift of 3 units up. So 1, 2, 3, 4, 1, 2, 3, and my final answer will be in blue here. There it is, the graph in blue. So we can take that stage by stage. You might be able to skip from the red graph to the blue graph if you can picture it. All right, let's do the next one. H of x equals 1/2 the cubed root of x minus 2. So let's draw our xy axes here. And after we draw that, we're going to go ahead and draw our parent graph here in red. So our parent graph is the cubed root function, which looks like this. And it looks like we do have, we don't have any kind of reflecting. There's no negative up underneath the cubed root here. We don't see a negative sign there, nor do we see one out in front here that would reflect it. So we do not have a reflection. So let's go to compress or stretch. If we go to this page, it says, okay, if the value c is out in front of the function, which is what we have, and c is between 0 and 1, which is what we have here, 1/2 is between 0 and 1. So you put a 1/2 in here. Then we have a vertical compression by c. So vertical compression by c. So that means we have a vertical compression by 1/2. And so back over here, let's go ahead and graph this thing. All right, so vertical compression by 1/2, it's going to take this red graph and compressing it by 1/2 is going to shrink it up in that direction, compress it. Here's what's happening here. As you plug in values for x, the 1/2 out in front will cut that y value in half from the original. So it gives you an idea of what it'll look like. It's going to also, we do see that there is our third step on here, a shift to the right of 2 units. So this value at 0, 0 is going to get shifted to the right 2 units. And then the compression, we're just going to draw a generic compression here. It's going to make this thing, as you go out farther to the right or to the left, the y values will be half the value of the y values from the parent graph. All right, third one on here. It says g of x equals absolute value of 2x plus 4. First thing I'm going to do here is get this into a format that matches our examples up here. We want to take and factor out a 2 here, x plus 2, so that this function looks like some value c times x in the absolute value. So it's kind of the form absolute value of cx, and that will help us when we get to the compress or stretch part of this. We'll go ahead and draw our xy grid. This is an absolute value function, which looks like this. Here's the parent graph. And there's no reflection. We don't have any reflection. There's no negative sign out in front of the absolute value, nor is there a negative sign in front of the 2 that you see in the absolute value. So we don't have any kind of reflection. Compression or stretching, that is happening here. There's a compression or stretch. Let's go to our other page here, or look at you're looking at your table, it's right there, but I have absolute value of cx falls into this category right here, f of c times x. We have the cx inside the absolute value, where the function f of x is, the parent graph is f of x equals absolute value of x. So it says if c, which in this case c is 2, so 2 is greater than 1, we have a horizontal compression by 1 over c. So 1 over 2 will be our horizontal compression. Horizontal compression is going this way. So what that's going to do is make that graph narrower by half. So going back here, down to the bottom, it's going to take this graph and make it a little bit narrower by half. So instead of being at 0, 0 in the parent graph, well, 0, 0 is going to stay the same, but instead of going to negative 1, 1, it's actually going to go, let's see here, negative 1, plug in a value if you want. If you plugged in negative 1 to the graph here and compare it, so if we have absolute value of 2 times negative 1, my output would actually be 2. So at negative 1, I'm already 2 up, and you'll see that that will give it the effect of horizontally compressing it by half. If I were to plug in a 1, I would get a positive 2. If I plugged in a 1, I would get a positive 2. And I think that's probably enough. If I just connect the origin to those, you'll get an idea of what the horizontal compression does to that parent graph. So I have one more thing to do here, and that is, third step is shift this by 2 units. So that's going to take my green graph and shift it over 2 units, and I'm going to try to copy it as accurately as I can. So a little skinnier or horizontally compressed graph from the red one. So blue is my final answer. There it is. So once again, if you want a consistent method for doing these, do the reflections first over x or y, do the compressions or stretches, and then do the shift. All right. Moving right along on number 4 here. It says write a rule for the function by taking the parent function and performing the transformation. So you're going to be given a description of the transformations, and you're going to write a rule. So it says, if f of x equals 1 over x is the parent graph, shift 3 units right, stretch vertically by a factor of 5, and shift down 6 units. So shifting 3 units right would mean replacing x with x minus 3. So we would take this 3, place it in here, and let's see, it says 3 units right, so we put a minus sign in there. Yeah. Get that excellent. So x minus 3. And then it says stretch vertically by 5. So stretching vertically by 5 is going to multiply this by 5. And then shift down 6 units is going to take the whole function and subtract 6 from it. So in the end, here's what this looks like. You can maybe put a dot up here between the 5 and the 1. So we have, in the end, let's call it g of x equals 5 over x minus 3 minus 6 is my final function that has those shifts in that vertical stretch. All right, B, a of x equals int x. That's the greatest integer function. Greatest integer function is the step function. What it does is it takes and pulls back any value you plug in, so to the previous integer. So for example, if you plug in 0.1, it would give as an output 0. If you plug in 0.5, it will give 0, so forth and so on. So we have a closed dot here, and then we go over to 1, and then an open dot there. Because if you plug in 1, what it's going to do is jump up to 1, 1. And if you plug in any value between 1 and 2, but not including, so there's 1 right there, there's 2, 1, 2, but not including 2, it's going to give you an output of 1. It's going to pull back to there. And you just keep on going like that. So put a 3 on here. It's going to jump up to the next step, close circle, open circle. So, and then here, down here at -1, put a value there, look like this, open circle on the right, closed circle on the left, connect the two. So there's our step function. So we're going to reflect this about the y-axis. So we're going to take these stair steps and reflect them over the y-axis, picture flipping this over the y, and compress horizontally by 1/3 and shift up 3 units. So what will happen here is the reflection about the y-axis would be a negative value. So if I were to take this int x function, I'm going to have to plug a negative value in here for x. That's the reflection. And it says compress horizontally by a factor of 1/3. If you look at this page right here, oops, gotta go the other direction. So compress horizontally by a factor of 1/3. What that's telling me here is that if I have a factor of 1/3 for a horizontal compression, then C must equal 3. You can see it here. So what we will have is actually a 3 in front of the x in the greatest integer function. And because of the reflection, it's going to actually be a -3. Actually, I keep doing that here. Let's go back to the right page here. We got to go forward on this one. All right, so we're plugging in a -3 here. So looks like this. C is would have to be 3 for you to have a horizontal compression of 1/3. And then we have a shifting up of 3 units, so we would then add 3 to this. I can't fit this whole thing in here, but what's happening here is I have 1 over 1/3 in this int x thing, and that becomes 3. And it's negative because of the reflection about the y-axis. So we have 1 over 1/3. Think of that as -3. So my function would look like this. A of x, in blue here, A of x equals -3x plus 3. And there it is. So that is the greatest integer function, reflected about the y-axis, compressed horizontally by 1/3, and shifted up 3. All right, it says use the graph of the function f to sketch g. So here I'm giving you a generic function f. It is not one of our parent graphs on your yellow sheet. It's just this really piecewise function made up of linear segments. And we're going to go ahead and redraw it using the information given here. So look at the first one, A. It says g of x equals f of x plus 3 minus 2. There's no reflection. There's no negative out in front of f of x, nor a negative inside the parentheses there. So there's no reflection. There's no compression or stretch. because there is no value coefficient other than 1 in front of the x. So we just have a shifting going on here. So we're going to shift this graph 3 units left and then 2 units down. So I could take any of these points. I could choose this one right here if I want to. Move it 1, 2, 3 units left and 1, 2 units down. And that's where my new green dot's going to go. So I can erase this one here. So this point just moved to here. And this point right here that I just put a dot on is going to go also 3 left, 1, 2, 3, and 2 down. And so the new endpoint is right there. So let's go ahead and draw that. The graph comes up. There's the peak right there. And then this value right here is also going to go 1, 2, 3 units left and 1, 2 units down and land right here. So there's the new spot there. And then this one right here is 2 units to the right of that one, so I can probably just fill that in. So there's the first one, A, the green one. All right, B, there is a reflection for B. So we're going to take this shape and we are going to reflect it and then also stretch it. So I'm going to do this in 2 stages here. Let's just do the reflection first. When you reflect over the x-axis, that's what this says, reflect over x, this is going to remain here. This point right here is 1 below the x-axis, so it's going to move to right over here. Matter of fact, let me do this. There it is. It goes from here to here. And then this value right here is going to move right up over. Oh, okay. See if I can grab. Okay, so let me grab it, move it right there. And then this value that was over here, see if I can grab just that point. I don't know if it's going to let me. There it goes. And that's going to be 2 units above the x-axis because it was 2 units below it there. So there it is. That's just the reflection. Okay, so let me do a dashed red line, and we'll do a solid one when we get our final answer. Okay, so there's a dashed red line. That's just the reflection. Now we've got to do a compression or stretch with that -2. So actually, forget the negative there. Let's just take 2. Go back to our chart here. We have a 2 out in front, so it falls into this category over here. Let's erase all this stuff. So it's a 2. This is a 2 now. It says if C is greater than 1, so 2 is greater than 1, we have a vertical stretch by 2. So we have a vertical stretch by 2. That means going back to here, vertical stretch by 2, that means each value is going to be multiplied by 2, at least the y value. So you see this one right here? It's at 2 units above the x-axis. It's now going to move to 4 units above the x-axis. So 2 times 2 is 4. The one that's sitting at 0 on the x-axis has a y value of 0. If I multiply that by 2, it's going to stay right there. So it remains right there. This one that's 1 above the x-axis will end up 2 above the x-axis. And same thing with this one. So my new and final picture here in red, we'll do in solid, looks like that. So there it is. I'm going to erase the dashed one. It's just there to help me. All right. C, we have f of -x plus 3. The negative in here says reflect over y-axis. And so I'm going to do that first as a dashed line. I'm going to reflect this over the y-axis. So here I have a point that's 1, 2, 3. This one is 4 to the right here. It's going to move it 1, 2, 3, 4 to the left over here. So that'll be the new point. So just take this point right here. If it'll let me, well, maybe not. And move it 4 units over. And then this point right here, which is just to the left, 1 unit to the left of the y-axis, is then going to move 1 unit to the right. So there it is. It's a new point there. And let's see. So we've moved this point, this point. This point right here, it's 2 units to the right of the y-axis. It's going to move from there to 2 units to the left. And so maybe some of you can just visualize this and take care of it that way. The final one here is, so I have this little segment here, and then it goes up to here. So I have this, that, or I should be doing this as a dashed line. Let's do that. This is not the final answer just yet. And then what's going to happen here is this segment right here is going to get reflected over. If you just think of this point right here as being 1, 2, 3, 4 to the left, it's going to go 1, 3, 4 to the right. So let me erase that. Backfill this in. Make this dashed, bigger dot here. Make this guy dashed. So we went from here to here, and then here to here. There. So there it is. That's just reflecting over the y-axis. We have that dashed line. Then we're going to move everything up 3 units. So counting from here up 1, 2, 3 units, and 1, 2, 3 units, 1, 2, 3 units, and let's see, 1, 2, 3 units to right here. So in solid here is my final answer for the blue one. I'll go back, erase some of this stuff. Redrawing my red one here. There it is. So there are the 3 solutions to those graphs. All right, last one here. It says FedEx's overnight delivery is $18 for a package less than 1 pound, $21 for one weighing at least 1 pound but less than 2 pounds, $24 for one at least 2 pounds but less than 3 pounds, and so on. Write a function for the cost, C of x, of shipping a package weighing x pounds. This is my attempt to show you what it looks like, or how we might use a greatest integer function to model. So here we have 1, 2, 3, and right here we have $18. And then the next jump up was 21. And the next jump up was 24. So what's happening is if it's less than 1 pound, it's less than 1 pound, it can't be 0 pounds, but if it's less than 1 pound, between 0 and 1 pounds, we'll say it's $18. If it's 1 pound but stays less than, between 1 pound inclusive but less than 2 pounds, the cost is $21. And then less than 3 pounds but at least 2 pounds would be right up here at $24, and it just keeps on going. So we're asked to write a function for the cost, C of x. So we have C of x equals well, first of all, we can see that it starts at $18. So somehow we've got to jump our basic parent function of the greatest integer function from being on the 0 between 0 and 1 to up to 18. So you're going to have a plus 18 in there. There's a vertical shift of plus 18. Also, the int x function doesn't look like it's reflected at all, but it is getting stretched because remember our basic parent function drew up here for this guy. It's right here. I mean, it's at 0. Let's see, we got 0, 1. You can see why I had to move it up 18, but it's starting at 0, then goes to 1, and then 2, and so forth. Well, this one, starting at 18, and then it's jumping from 18 to 21, and 21 to 24. So it's been stretched vertically. Instead of by 1, it's by 3. So we have 3 times int x. And this is one of those ones where it'd probably be a good idea to test it here on our calculator. So if we take and plug in int of, say, 1. So int 1 would be finding C of 1, would be 3 times int 1 plus 18. We know that int of 1 is going to give me the value 1. And so we have 3 times, try it on your calculator if you want, plug in, go to math, num, int 1, can see it on the graph up here. If I plug in 1, I'm going to get as an output a y value of 1. So int 1 is 1 plus 18, and that gives me 3 plus 18, $21. So the 3 was the correct vertical stretch there. So there's my function. We'll box it here that models FedEx's overnight delivery fees. All right.